Now we continue with the third section of this chapter, which is solving equations. Well, solving equations isn't that hard. You have learned how to solve equations in grade 7, 8, 9, 10, and 11. The most important part, which we might have problems with, is using quadratic equations as the ones that you see over here. The first equation, 3x squared plus 4x plus 1, is a quadratic equation in x, okay? Which can be solved by calculating delta, which is b squared minus 4ac. However, in physics, we can skip this step and go directly to the calculator and get the answers from the calculator. I'm not going to do that. You can do it by yourselves as an application. If you have any problems, I will show you later how to log into the calculator and find the solution of such equations. Now I'll stop at b a moment. In b we have t power 4 and t squared. What should be done in order to solve this equation? Basically, we change t squared to x. Now the equation becomes x squared, because t4 is t squared squared, plus 4x minus 5 equals to 0. Now we can use the calculator, or we can use the fact that 1 plus 4 plus minus 5 is 0. Then directly x1 is 1 and x2 is c over a, which is minus 5. Now back substitute. T squared equals to 1, meaning t is plus or minus 1. T squared is minus 5, no real solutions. So this was just a summary about the method to solve quadratic equations. Now, a point concerning quadratic equations is using the sum and product. If you are given the sum and the product of two numbers, you can insert them in this equation and find the result. And speaking of sums and products, an idea comes to my mind, which is when the sum of two numbers is constant, their product is maximum when these numbers are equal. Take, for instance, 4, 8, 5, 7, 6, 6. These three pairs of numbers have a sum of 12. However, if you multiply 6 by 6, you get the largest product. So a product of two numbers is the maximum when they are equal, given that these numbers add up to give a constant value. This is just a note. If you know it, it's good. If not, it's just an additional information. Now we go to the real deal, derivatives. What we are interested with now is the meaning of a derivative and how should a derivative be calculated. So first we go to the analytical definition, in which a derivative is said to be the variation of a function relative to the variation of another variable. For example, if you consider this line, y equals f of x, that's a function, y as function of x. When you say y prime, which is dy by dx, you are simply calculating or determining the variation of y relative to the variation of x from the way of writing it. Now, when you use dy by dx, then this variation is infinitesimal. dx is too small. Graphically speaking, when we say y prime is dy by dt, it is simply the slope of the tangent to the curve. Usually the derivative is evaluated at a point. Thus, when we say dy by dx or y prime at a point, that represents graphically the tangent to the curve at that particular point. Let's take an example in physics. Before we go there, if the variation is linear, then the derivative is the slope of the line itself. We don't have a tangent. Okay, now we go to the application. Speed is defined as the rate of change in distance relative to the change in time. By just following the definition, rate of change of distance with respect to time. Now take that delta t to be small, tending to 0, then you get dx by dt. Thus, we can say that v equals x prime. You notice that we can say x prime or x dot. Usually we use the term dot to indicate the derivative with respect to time. Now, in a graph x of t, the speed at an instant is the slope of the tangent. What does that mean? Check this graph here. X varies as function of time t. The graph showing the variation shows different positions of x at different time instance. Now, if at a certain particular time t1, we trace 2 points very close to each other, notice they're not the same point, they are very close to each other, and we join them, this line is almost, I can add the term here, almost tangent. The slope of this tangent is simply the speed. What I can tell in this figure is that the speed is positive in this situation, simply because the slope is positive. Now, passing to another harder term in mathematics, which is the primitives, or simply antiderivatives. Usually we study primitives or antiderivatives in grade 11. However, we study that at the end of the year. Most probably you have not seen this before. Some people have enough time, so they cover it. For those who didn't study primitives, this part should be of minor importance. It's not very important. Later on, you study it in mathematics and you feel it's easier. You don't need to worry a lot about it concerning physics. When we say antiderivative or primitive, by the way, the term antiderivative makes it easier to understand. The primitive of a function y equals f of x is another function, capital F of x, such that the derivative of the capital F function is small f itself. The notation of primitive is when you use this symbol, which is like a bar. In fact, if you look and focus closely, you'll notice that it's nothing but letter S, which is stretched. So, f of x, capital, equals primitive or integral f of x dx. The antiderivative or integral of a function is the infinite sum of areas of rectangles of length f of x and width dx. This might be a bit tricky for a regular student, especially that you have not seen it before. What does that mean? Before we move to the symbols here, if I have a function here x and y, and here is a graph. If you consider this part here under the graph, it is almost rectangular. Now at the middle, draw a bar. You have now a rectangle. Now in this rectangle, you notice that there is a slight part above. Let me increase the size. Okay, so suppose I'm considering here and here. At the middle, we have drawn this. If I color these, I obtain a rectangle of length f of x and width dx. dx is nothing but delta x. However, delta x is too small. To calculate this integral, you can either calculate areas or follow these analytical equations. Integral of sum is the sum of integrals. If you're integrating x to the power m, it is 1 over m plus 1 x power m plus 1. For example, integral of x dx is x squared over 2. Integral of x squared dx is x cubed over 3. Okay? Now, when you add boundaries to the integral, you simply evaluate it once on the upper boundary and once on the lower boundary. Graphically speaking, in the graph showing y as function of x, this is very important. The primitive or antiderivative gives the area between the function and the x-axis. Let's check this example. Once you understand the example, it's more than enough. Integrate f of x from 2 to 8, where f of x is y equals x plus 4. Okay? How to integrate this? If I use rules of integrals, integral of x or primitive of x is x squared over 2. Primitive of 4 is 4x. ask yourselves, what do I derive to get 4? It's simply 4x. What do I derive to get x? It's x squared over 2. Now this answer should be evaluated at two values, 8 and 2. At 8 we replace the values, at 2 we replace the values, we subtract or do the mathematics here, you get 54. On the other hand, if I go to the graphical meaning of primitive, which is the area under the curve, integral fx to 8 is the area under the line y equals 4 of x, which 4 plus x, which you can see over here. The area is shaded in yellow. To calculate the area, I simply calculate the area of a trapezoid, which is height times large base plus small base divided by 2. The height is this, which is 8 minus 2, 6. 8 minus 2, 6, it's somewhere, yes, it's here. However, if you want to calculate the base, which is this part, it is this value here, which is y for x equal to 2. Then we have y for x equal to 8, and that's it. X equals 2, y6, x equals to 8, y12. Now, replacing all these values, we get exactly the same result. When you calculate primitives, you simply calculate areas. Choose the easier and apply it. That's it. By this, we come to the end of this section, in which we have focused on derivatives and primitives. We studied the equations as well. Now, before we end up, I just would like to remind you that anyone who faced problems understanding primitives, don't worry about it. All you need to know is that there is something called primitive, which is an antiderivative. It can be calculated by some complicated mathematical equations or by finding the area under a curve if it's given. Okay? In the upcoming section, we're going to talk about these more, but we're going to focus on the applications in physics in a simple task. Okay? Thank you again for your time and see you in the upcoming lecture.